Have you ever flipped a coin and watched it land flat on a table? That definitive result, heads or tails, is exactly how our computers think. They operate on absolute certainty. Every text you send, every video you stream, and every website you load is built on this simple logic. Inside your device, billions of tiny switches are either flipped on to represent a 1 or turned off to represent a 0. This system is incredibly fast and highly reliable. But the physical universe doesn't operate in such rigid black and white terms. Down at the smallest levels, things exist in complex, overlapping states of possibility all at the same time. Because our standard computers are built to only understand an absolute yes or no, they are physically incapable of processing a mathematical state of maybe. Imagine calculating the exact state of that coin, not resting flat on the table, but while it is still spinning rapidly in midair. That spinning motion represents a state of overlapping possibilities. Before the coin lands and we look at it, it carries the weight of being both heads and tails at the very same time. How do we force a rigid, everyday computer, one that only speaks in absolute ones and zeros, to understand and process this spinning, multidimensional state? Bridging that massive gap between absolute stops and overlapping spins is the specific purpose of a new mathematical framework called Qx. Normal computers organize data into a flat horizontal line, forcing every 1 and 0 into a rigid sequence. Qx changes this by breaking that line apart and stretching it into a two-dimensional grid, giving each bit its own specific place in space. This hand-drawn diagram shows the creator conceptualizing this exact geometric transition. You can see the traditional flat binary chain at the top, contrasted directly with the clustered, circular patterns of a quantum chain below it. Upgrading to a spatial grid provides the mathematical room necessary to map the complex, overlapping variables of a spinning coin. A flat line simply cannot hold that much dimensional information. Instead of placing an absolute 1 or 0 into this new grid, the QxBin Framework plots mathematical fractions. This fractional math directly represents the physical wobble of the spinning coin. It calculates exactly how much it leans toward heads versus tails. This document shows the specific mathematical proof used by QxBin. It identifies the basic states, labeled here as B0 and B1, as symbolic fractions, which are then elevated to varying mathematical powers to map out the probabilities. Trading rigid whole numbers for shifting fractions allows a standard computer to represent a state of maybe. The math we already use suddenly gains the flexibility to process that spinning reality. To make this useful, the theory has to connect to reality. QxBin does this by linking its math to physical computer hardware, specifically using magnetic Hall effect sensors. Unlike a standard mechanical keyboard switch that only recognizes a complete click on or off, these magnetic sensors measure the exact partial pressure applied to a key. This text, titled Mapping Physical Coin Toss Dynamics to Amplitudes, outlines how these analog partial measurements provide the physical wobble data. That data is fed directly into QxBin's matrix to calculate the exact state of the spin. QxBin is a practical bridge built specifically to be read and executed by tangible, everyday input devices right on your desk. Right now, true quantum computing requires extreme, inaccessible environments, like sub-zero vacuum chambers that look like giant chandeliers. This shuts out everyday people from experimenting with the technology. Because QxBin relies on standard matrix fractions instead of specialized quantum physics, it can simulate quantum logic entirely on normal, room temperature hardware. This handwritten note shows the creator's ultimate goal, using this accessible math to give anyone with a standard computer the power to simulate qubits, those complex building blocks of quantum logic that usually require massive labs. By acting as a universal mathematical translator, QxBin finally allows our standard flat-line hardware to speak the complex spinning coin language of the quantum universe.